Welcome to this next video in the playlist on group theory. In this video what we're going to talk about is groups of order a prime natural number squared, and we're going to completely characterize the isomorphism classes for groups of these orders. Okay, so what we're effectively going to do is analogous to what we did long ago in this playlist on group theory for groups of order a prime natural number. We saw long ago that if you've got a group which has order a prime natural number, then that group is forced to be isomorphic to a certain group, namely the cyclic group on the set of P elements. Okay, so there's only one isomorphism class of groups of order a prime natural number, and indeed if you've got any group of order a certain prime natural number, they're all isomorphic to one another. All that's different between them is different symbols. What we're going to do in this video is the analogous thing for groups of order a prime natural number squared. Okay, so we're going to be having some group, capital G, which of course is going to be a finite group now. Okay, and its order is going to be a prime natural number, which I'll denote P squared. So examples are, of course, you could use as your prime number 2, and therefore the order of the group could be 4. So what we're going to do will apply for groups of order 4. We could use P is equal to 3, so what we're going to do will apply for groups of order 9. We could use P is equal to 5, so it will apply for groups of order 25. Then we could do it for 7, groups of order 49, etc. Okay, so all of these sizes of groups where it's a prime natural number squared, we are going to completely characterize which isomorphism classes exist for these groups of these orders. Okay, so I'm going to give the results straight away, and then we'll spend the rest of the video trying to actually understand why it's true. So the result is that there's only 2 separate isomorphism classes for groups of order a prime natural number squared. So if you have a group of order a prime natural number squared, it's isomorphic to one of these 2. Okay, so the 2 are the cyclic group on the set of P squared elements. Okay, so Z P squared, or you could call this C P squared, it doesn't really matter, just different notation. Or the other isomorphism class is that it's your group will be isomorphic to the cyclic group on the set of P elements direct producted with the cyclic group on the set of P elements. So ZP cross ZP. Okay, so if you have a group of order P squared, the claim is that it will be isomorphic to one of these 2 options. So in a sense, these are the only 2 groups that exist of order P squared. So in the case of 4, the 2 options are the cyclic group on the set of 4 elements, and then Z2 cross Z2, which is of course the climb 4 group. Okay, and then it generalizes for 9. The 2 options are Z9, the cyclic group on the set of 9 elements, and then the cyclic group on the set of 3 elements direct producted with the cyclic group on the set of 3 elements. Okay, but those are the only options. Okay, so we will come on to proving this. However, before we can actually prove this, we're going to need to know a prerequisite. So we're going to start with a prerequisite, and the prerequisite is a little bit of understanding about P groups. Okay, so the prerequisite theorem is applicable more generally than just for groups of order a prime natural number squared. It applies for all P groups. So let me firstly just remind you what a P group is, and then I'll describe the theorem that we need to know in order to go any further. So firstly, what is a P group? So a P group is usually denoted capital P rather than capital G. Okay, and it's any group that has order a prime natural number squared, not squared, to a power of a natural number. Okay, so more general than a prime natural number squared. So a P group has order a prime natural number, which once again I'll denote P, so 2, 3, 5, 7, 11, 13, 17, 19, etc. Any of these prime natural numbers to the power of some natural number. So alpha here is a natural number, a counting number. 1, 2, 3, 4, 5, 6, whatever. Okay, it's not 0 though is the point, okay? A group of order 1 is not counted as a P group. Okay, right, so that's the definition then of a p-group, and the theorem that I'm about to give works for arbitrary p-groups. Of course, if I've got a group of order p squared, that is a p-group, but of course this theorem is more general. It works for p cubed, p to the power of 4, p to the power of 5, so that's why I'm just stating this definition of p-groups, because the theorem that I'm about to give applies for arbitrary p-groups, but we're of course going to apply it to groups of order p squared. Okay, so here comes this really important theorem that we need to know in order to go about proving that the only two isomorphism classes of groups of order p squared are this one and this one. Okay, so here comes what we might call Theorem 1. Okay, right, so Theorem 1 is that the centre of a p-group is non-trivial. So let me firstly just write a little bit of setup, a little bit of introduction. So P is going to be a p-group, so the order of P is going to be some prime p to the power of alpha, where alpha is greater than or equal to 1 here. Okay, then the claim is that if you look at the centre of this p-group, so claim, if I look at the centre of the p-group, which is denoted z of p here, okay, then it is not equal to the trivial subgroup, which I will denote by 1 here. Okay, so the centre of a p-group is always non-trivial, is the theorem that I want to prove to you now. Okay, so to start with, let me just remind you of what the definition of the centre of a the centre of a group is. Never mind a p-group. What's the definition of the centre of a group? Okay, so the centre of a group, and I will stick with using my notation for a p-group here, although this applies for a more general group. Okay, so the centre of a group is all the elements of the group. So all little g is an element of your group, which in this case is being called capital P, such that these elements that are in the centre of the group commute with every other element in the group. So g composed with s must equal s composed with g for all other s, which is an element of the group. So you have to go through every single s, which is an element of your group, and check for this element g that g composed with s is the same as s composed with g. And if that's true for all s, then you can put little g into this set. So you go through every element of the group and you check, does it commute with every other element of the group? And if it's true that it does, then you stick it into the centre of the group. So it gets this special privilege of being in the centre of the group. Now the centre of the group is always non-empty because the identity element always does commute with all other elements of the group. If you stuck in the g here, the identity element, of course that statement would be true no matter what s you took from the group capital P. So the identity is always in the centre of the group, so it is always non-empty, and in fact it always forms a subgroup of the group. Okay, so the centre of the group will be a subgroup of our group, which in this case is, of course, a p group. Okay, but this all holds true for more general groups than just p groups. So this is all done in the context of the p group, but it all applies for more general groups. Okay, and if you're not so familiar with that, I believe I do have a video earlier in this playlist on group theory entitled The Centre of a Group. Okay, right. So what we want to prove then is that the centre of the group is not just the trivial subgroup. It contains more than just the identity element, because in some groups it will be the case that the centre of the group just contains the identity element, and therefore will just be the trivial subgroup. What we want to prove is that if you've got a p group, a group that has order a prime natural number to some power, then you can instantly conclude that the centre of the group is non-trivial. Okay, and therefore, going back to our groups of order p squared, we can conclude that the centre of those groups is going to be non-trivial. Okay, so how am I going to prove this? Well, I'm going to prove this using the class equation. Okay, so let me just remind you of what the class equation actually is and where it comes from. So remember the class equation, which is something that I have a video on earlier in the playlist on group theory. The class equation comes from considering a group action of the group on itself that you can establish for an arbitrary group capital G, but again we will do it in the context of our P group. Okay, so for a general group, what you can do is you can create a group action where the elements of the group act on the elements of the group. Okay, so G and A, G acts on A, G and A are both going to be from the group. Okay, and the way that you define this is that you'll just send A onto the G conjugate of A. Okay, so to draw a picture of this, here will be our group action composition table, so it'll be dot here, and I'll just colour it in pink here, and the set on which the group is going to be acting will be the group, and of course the group that's actually acting will be the group as well. So down here, obviously, we put all of the elements of the group, which are the elements that are actually doing the acting. So this will be your little g, if you like. Okay, so here, let's say this is little g here, and then again up here in all of the columns you'll put all of the elements of the group, but of course up here this is in the context of just being a set which is being acted upon. Okay, so I'll just put this is taking the place of the set in the group action, and this is taking the place of the group. Okay, so here now, an element in here I'm denoting by little a, and then the answer to what G acting on little a is will be defined in terms of the composition law that is on the group. All you'll do is conjugate little a by G. Okay, so this is perfectly definable. You can build this group action composition table, and indeed in the video on the class equation previously in this playlist, I imagine I will have proven that this group action is indeed a group action, as it obeys the two axioms that a group action needs to obey, i.e. Compatibility with composition and the fact that the identity element will map all elements of the set onto themselves. Okay, so this is a group action though. And now what we can use it to do is we can use it to partition up the set on which it's acting. So of course, for an arbitrary group action, one of the great things that you can do, what you can use it to do, is partition up the set on which the group is acting into orbits of that group action. And what we can do is apply that here. So of course, the set on which the group is acting is just the group itself. Okay? So here is our group, and again I'll go back to using my notation in the context of the P group, but again this does apply for an arbitrary group. So here's my group, capital P, okay, and I'll just colour it in red here. So what I can now do is partition my group, capital P, up into the orbits of this group action. Now, the orbits of this group action are going to be all of the elements that can be mapped onto each other by being conjugated by elements of the group. Now some, i.e. they're going to be what we would call the conjugacy classes of the group. We're partitioning the group up into its conjugacy classes. Okay, now some of the conjugacy classes will be very, very small and will just contain single elements. Okay, and these will be the elements that are in the center of the group. Okay, so if you are in the center of the group, then you commute with all other elements of the group. So when you try conjugating any element of the center of the group, so let me just show this. So if, let's say, Z is an element of the center of the group, if you conjugate that element by an arbitrary element of the group, okay, of course this will commute with all other elements of the group, so you can just swap G and Z around here, get that this is Z, G, G inverse. The G and G inverse will now cancel, so this will just become Z. So when any element of the center of the group is conjugated by any other element of the group, it has absolutely no effect. It's sent onto itself. So if I've got an element of the center of the group here, okay, Z up here, then this entire column here will just consist of Z, Z, Z. All of the answers will just be Z, because no matter what you conjugate Z by, it will always just be mapped onto itself. Okay, so therefore any element of the center of the group, including the identity element, will be in a conjugacy class on its own, an orbit for this group action on its own. So these are meant to represent these little orbits that contain single elements which are all in the center of the group. So this collection of one element orbits, singleton conjugacy classes if you like, those are the elements of the center of the group. Okay, then you might have the more interesting conjugacy classes, the non-trivial conjugacy classes over here. Okay, like so, that contain more than one element. Okay, so these elements will, they won't be in the center of the group, and therefore when you conjugate them by certain elements of the group, you may well now get some more elements, and therefore their orbits will consist of more elements. And then what the class equation basically says is that the order of the group, and again this can be applied for an arbitrary group, but I'm doing it in the context of my P group here, the order of the group is equal to the order of the center of the group, so how many elements are in the center of the group, okay, that makes sense, plus the size of all of these non-trivial conjugacy classes. So plus the sum of the size of the non-trivial conjugacy classes, and I'm using this notation here, so C for conjugacy class and then subscript GI, where these GIs are just going to be representatives of the non-trivial conjugacy classes. So sum from I is equal to 1 to R. So G1, G2, all the way up to GR. These are just representatives of the non-trivial conjugacy classes. So maybe this one has G1 in here, this one has G2 in here, and it will go on all the way up to the final one here, which will have GR. Now in this case, of course, there are 8 non-trivial conjugacy classes there, but more generally, it could be an arbitrary finite number. Of course, it will be finite because we know that the order of this group is finite, so you can't end up with an infinite number of conjugacy classes inside there. Okay, so you take a representative of each conjugacy class, and of course you construct the conjugacy class for that, take its order, and then sum them all up, and then when you do this, you'll get the order of the entire group overall. Okay, so this is the class equation. That's just a reminder of the class equation. Now, what are we trying to prove? We're trying to prove that the center of a P group cannot be equal to the trivial subgroup, i.e. we're trying to prove that the order of the center of the group is not equal to 1. Okay, if we prove this, we prove this, because we prove that there's more than just one element inside of this, i.e. it cannot just contain the identity element. Okay, and that's why the class equation is going to be useful to us, because of course here appears the order of the center of the group. Okay, now note, we know that this is not 0. Okay, at the very least contains the identity element, so it must be greater than or equal to 1. Okay, so where to now? Well, now we have to somehow use the fact that we're working with a P group here, because all of this is just true in an arbitrary group, okay? It's not true in an arbitrary group that we can conclude the center of the group is not equal to the trivial subgroup, so something about it being a P group must make this true, so we're going to have to use the fact that we're in a P group. So firstly, we can replace the order of P here with P to the power of alpha, i.e. a multiple of this prime number. That might be useful. Okay, now let's have a look at this. The order of the non-trivial conjugacy classes, okay, or rather the sum of the orders of all of the non-trivial conjugacy classes. I claim that these are all going to be multiples of P as well, and that's going to lead us to being able to conclude that this is not equal to 1. Okay, but firstly let me show you why all of those are multiples of P. Okay, we now apply what we haven't yet applied, which is the orbit stabilizer theorem for this group action. Okay, so we know that the size of an orbit, which in this case is the size of a conjugacy class here, okay, times the size of a stabilizer. Now, what will be the stabilizer of the element GI? So we're using this representative of the conjugacy class, so we'll use that as the element that we want to construct the stabilizer for as well. Okay, the stabilizer will be all of the elements of the group here, which when they conjugate GI, gives GI back again, i.e. that's what we would call the centralizer of GI in G, like so. Okay, a subgroup of G, and this is just by definition all of the elements of G. All little g is an element of capital G, such that if I conjugate, if I use little g to conjugate little gi here, and I apologise for little g being used so much here. So if I use little g to conjugate the element that I'm interested in here, okay, I should have called this something else, but never mind. I must get little gi back again. Okay, so it's all the elements of the group, which when they are used to conjugate the element of the group of interest here, fix it, basically. They give it as the answer. And of course, that's just going to be the stabilizer of this element under this group action. Okay, so the order of the orbit containing GI times the order of the stabilizer of GI in the group must equal the order of the group that's acting on us. Okay, and of course I've changed my notation here, so I'll just make that P again so that it applies for our P group here. Okay, it does work for an arbitrary group, but we're working with this P group, so I'll replace that there with P. Okay, it must be equal to the order of the group here, P. Okay, and this of course is equal to P to the power of alpha. Now, we know that this is not equal to 1. The order of the conjugacy class of GI is not equal to 1, because otherwise it would be one of the trivial conjugacy classes. It would mean that that element GI was in the center of the group. Okay, so this must be bigger than 1. But look, this times this must make some power of p. That means that all this can be is some power of p. Okay, so this is going to be a multiple of p because it must divide p to the power of alpha. This times this must make p to the power of alpha. That means if this is not equal to 1, it must just be a power of p. In particular, all I need is that it's a multiple of p. Okay, so what have I managed to conclude then from the orbit stabilizer theorem? I've managed to conclude that all of these non-trivial conjugacy classes that I've divided my p group here up into have order a multiple of p. So when I'm adding all of these orders up, I'm still going to end up with a multiple of p. When you add loads of multiples of p together, the p just factors out. Okay, of course, from your knowledge of classical algebra, you know that. You don't need to know anything about ring theory to understand that. From classical algebra, you can understand that. You will still end up with a multiple of p. Okay, so when I add lots of multiples of p together, this great big sum is still a multiple of p. Okay? Now, why does that prove that the order of the centre of the group cannot be equal to 1? Well, because this plus this multiple of p is equal to p to the power of alpha, another multiple of p. If this was equal to 1, you'd be taking a multiple of p, adding 1 to it, and then somehow getting a multiple of p. That doesn't happen. Okay, if you take a multiple of p and add 1 to it, you don't still end up with a multiple of p. So this thing here must be a multiple of p as well. Okay, we know it's not 0, remember. We know it at the very least has to contain the identity. Okay, so we can now conclude from this that this must be a multiple of p, so that when we add these two things together, we still end up with a multiple of p. If it was 1, then you wouldn't end up with a multiple of p, and that would be a contradiction. So there's the proof, therefore, that the centre of the group does not have order equal to 1, and therefore is not the trivial subgroup when we're working with a p group. Okay, so to repeat this prerequisite theorem, if you've got a p group, a group of order a prime natural number to the power of some other natural number, okay, you can instantly say that the centre of that p group is not the trivial subgroup. It contains more elements than just the identity element, and we can apply this in the context of groups of order p squared, and indeed we will do after the break.